Hello, I'm Sana, and this is Lab 5, Faraday's Law. In this lab, we look at Faraday's Law and how it can be observed by dropping a magnet through a conductive tube. The induced current produces a magnetic field that exerts a force on the bar magnet. As a result, the bar magnet falls through the tube at a slower rate. Through this presentation, I will talk about the experiment of dropping a magnet through an aluminum tube to see Faraday's Law. I'll talk about the computational model of the experiment, and then I'll compare the data between the observed and the computational data. So the physics principles we use in this lab are Faraday's law, which is the integral of the electric field times the length. We also use Biot-Savart's law, which gives us a way to calculate magnetic fields, and the formula for that is mu naught over 4 pi times q times v cross r hat over magnitude of r squared. We also look at the concept of induced current, which is EMF over r, and then we look at Newton's second and third law. We know that as the magnet produces a force in the loop produces a magnetic field from the induced current. That magnetic force opposes the gravitational force the magnet experiences as it falls, and as a result, its descent slows down. To observe Faraday's law, we conduct an experiment where we track the amount of time it takes for the magnet to pass through the aluminum tube. Make sure that for the magnet you're using, the north side is facing down. You can find that using a magnetometer app on your phone. Repeat the trial 5 times so that you can find the average amount of time it took for the magnet to pass through the aluminum tube. In my experiment, I observed the fall time to be 1.58 seconds. Interpreting the simulation. Looking at a computational model, the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue are current flowing in opposite directions. Blue is a clockwise current and red is the counterclockwise current. If we were to flip the magnet upside down, the negative change in flux would point downward and the directions of the current would switch. Velocity, however, would stay the same. Looking at our results, it took 1.58 seconds for the magnet to fall through the aluminum tube in the experiment and 1.746 seconds for the computational model. Part of the reason they're different times is that the computational model doesn't account for environmental factors, like the way I dropped the magnet or the way I constructed my aluminum tube. The descent in velocity is shown on the plot on screen. You can see when the magnet is falling just due to the force of gravity versus when the magnetic force is acting against the magnetic force of the loop is acting on the bar magnet and slows its descent. So that's why you have that sudden spike and increase before it steadies out. Questions and conclusions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The magnetic force and current will increase while the velocity of the magnet will decrease. Resistivity is directly proportional to resistance. So if it decreases, resistance decreases. And if we look back at our formulas, current equals EMF over R. If R decreases, I increases, which means the current increases, and its resulting magnetic field and magnetic force will also increase. Since the magnetic force is increasing, it will act against the gravitational field at a greater magnitude, so the velocity of the magnet will continue to decrease. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, the magnetic force and currents will decrease while the velocity of the magnet will increase. Okay, thank you for your time and for listening to this lab. I hope this gave a clear explanation on the relationship between magnetic field, magnetic flux, magnetic force, and current, and the effect of Faraday's law in our environment. Okay, thank you for your time. Have a nice day.